Section 5.1, we are really going to get into what the definite integral is. And it's a really important tool in calculus for defining and calculating quantities that are important, such as areas, volumes, lengths of curves, different things like that, that we typically would not have a formula to do. The idea behind the integral is that we compute quantities by breaking them into small pieces, and then we add them up. And so we then consider what happens when more and more smaller pieces are taken. And finally, if the number of terms approaches infinity and we take the limit of these sums in, like we're going to do in section 5.3, the result is a definite integral. And what that really looks like is, if we're trying to take the area of this region, we don't have a formula to do that. So we get, so what you really have is, if you divided this into two rectangles, you would get an approximation of this area. And of course, we're over the curve that much, but we'd get an approximation. Then if we divided the area in region into four rectangles, we would get a little bit closer. The idea being that the more rectangles you get, the better, let's see, where is it? Okay, the better you would get, the closer you would get. And sometimes we can take the lower sum, which is what we've got here, and we've got an upper sum here. Do you see the difference? Because we stay under the curve, we go above the curve, and so that would be a lower sum approximation. This would be an upper sum. And there's some, just a table of comparisons. You can also do the midpoint, which I had, here is actually a midpoint, because you're using the midpoint of the interval as the height of the rectangle. So that was that. And then let's go look at the problems. We tried these in class, and I have a different approach than what we looked at in class, so we're going to go over that. I'm going to go over that now and see if it can make a little bit more sense. I actually had the right answers, and we thought, because it didn't make sense the way I was explaining it, of course. So now hopefully this will make sense and be a little bit better. All right, first question. We've got an interval from 0 to 8, and our graph is f of x equals 6x squared. We want to find an approximate area, lower sum, lower sum. So we want to do it with two rectangles and 4, and then we want to do upper with 2 and 4. So here's the process that I suggest we do. First of all, we want to get the length of our interval, which is actually going to be the width of our rectangle. So delta x, or the change in x, is 8 minus 0, and we said we're going to use two rectangles, so each rectangle will have a width of 4. So that's going to be important. So let's just remember that's the width of our rectangle. Okay, all right, so A part, we're going to do lower sum with two rectangles. We found this. So here's what I want us, let me make this a little bit smaller so I can fit it on here. All right, we're going to write the intervals as 0 to 4 and 4 to 8. All right, what I want you to do is take each interval and evaluate those endpoints. So in other words, f of 0 is 6 times 0 squared. F of 4 is 6 times 4 squared. Compare those two numbers you get, and we're going to choose the min because we're doing lower sum. Okay, lower sum means we're going to choose the min out of the endpoints. All right, so in the second interval, we've got 4 and 8. So we are going to evaluate f of 4. Remember, we're putting this into 6x squared. That's our function. So we're going to evaluate f of 4 and get 96, f of 8 and get 384. Choose the min in both of those comparisons. Then the area is these heights. These are your heights. 0 times that width of the rectangle plus 96 times the width, and we get 384. All right, let's do it with 4 rectangles. Our delta x ends up being 2 because we divided by 4, and so now our intervals are right here. So we are going to evaluate f of 0 and f of 2, f of 2 and f of 4, f of 4, f of 6, f of 6, and f of 8. And then we're going to choose the minimum value in each of those comparisons. So these were all the mins right here. And after you've done this, problem, and like the other ones, you won't have to figure all these out. I already knew what these were from the first part. So anyway, then I take my mins that I've gotten for the heights, and it's 0 times the width. So that's 0 times 2, 24 times 2, 96 times 2, 216 times 2. You ultimately get an area of 672. All right, C part. Now it changes the upper sum to rectangles. We still have this delta x. We have these intervals. Compare the endpoints, f of 0, f of 4. You get 0, 96. You get f of 4, f of 8. You got 96 and 384. But now we're choosing the max because we are doing the upper sum. Okay, so that means we're going to pick the max. These are our heights. So we have 96 times 4, 384 times 4. We get 1920. Same way with upper sum and 4 rectangles. Here's your intervals. Do your evaluations. You've already got those probably, most of them, because you've been working on those problems. At any rate, you're going to choose the max each time on these because you're doing upper sum. These are the heights of the rectangles. The 2 was the width of the rectangle because that was our delta x. So you have areas of each rectangle, 24 times 2, 96 times 2, etc. You end up with 1440. So that's the process that we're going to work. That's going to work for us best, I think. Hopefully that's going to make sense. So let's go to number 2. All right, this is the one where I got a little stumbled thinking that I didn't have it right, but I did, and so now I want to re-explain it. Okay, we're doing the same idea, but we've got this as our function, 8 minus x squared minus 2x. Our intervals for the A part, we're doing 2 rectangles, lower sum. Here's our intervals. So we're going to evaluate in the first interval, f of negative 4, f of negative 1. We get 0, we get 9. We're doing lower, so we're going to choose the minimum. We go to the second interval, which is negative 1, 2. We're going to evaluate negative 1 and f of 2. We get 9 and 0. We are still choosing the minimum. And so those are the heights of the rectangles. I know that sounds weird, but this is for our lower sum approximation. This is what we get. So those are our heights of our rectangles times the width. 0 times 3 plus 0 times 3. We do get 0 for the area for that one. All right. You're going to do the same thing with the lower sum and 4 rectangles. Delta x is 3/2. The intervals are here. And I went ahead and changed it to decimal. Because we can do that for this problem. So here's my intervals. In the first interval, evaluate f of negative 4 and evaluate f of negative 2.5. And I already knew what that one was, but I went ahead and plugged in the negative 2.5. I got 6.75. Same for this interval. I had to do negative 2.5 and negative 1. There's the min. I do it in the third and fourth intervals as well. Every time I'm choosing the min. All right, so those are my heights of my rectangles. My delta x was 3/2, so I had 0 times that, which was 0 plus 10.125 plus 10.125 plus 0. Your answer was 20.250. You do the same thing for the upper sum with two rectangles. Your delta x was 3. Here's my intervals. Evaluate at each endpoint of the interval, -4 and -1. You get 0, 9. You get 9, 0. You're choosing the max because we are doing upper sum. Okay, so you had 9 and 9 as the heights of your rectangles. You have 3 as the width of your rectangle. 27 and 27 is 54. Upper sum and 4 rectangles. Delta x is 3/2. There are your intervals. You evaluate each interval at its endpoints, -4 and -2.5. And by this time I have all these amounts because I've done them in the previous parts of the question. In each interval, you are choosing the max value. Between these two, you are choosing the max. Those are all your heights of the rectangles. 6.75 times 3/2, 9, etc. You get 47.25 for that area. Okay. Now, the one that we did, number 3, with the midpoints, was fine. I didn't have to change anything on that. You're given this function, x to the 4th. Here's your interval, divided into 4 subintervals. So I did that. And you're choosing the midpoint of this, and I didn't write that over here. Let's see, delta x is 4 minus 2 divided by 4, so that's 2/4 or 1/2. Okay, 1/2. So then we did the intervals. I added 2, and from 2 I went to 2.5, and from 2.5 to 3 I'm adding 1/2 each time. And then I found the midpoint between these numbers. That's in red. All right. So instead of evaluating anything else, we're going to evaluate the midpoints. So I have 2.25 to the 4th, 2.75 to the 4th, etc. Now I changed it to fraction because right here it tells me in my answer I'm going to type an integer or a fraction. So when you do this on your calculator, let's see, if you do 2.25 raised to the 4th, and you get this number, go ahead and go to math, enter, and get 6561 over 256. Go ahead and use your calculator to get the number, but convert it back to fractions. Okay, so these are the heights that we're going to use for our rectangles. This is the width of our rectangle. So we have height, length, or height times width on each of those, and we get this. These are our little areas. Then it asked us about average value. Average value. Okay, the average value, we're going to take the width of the interval, which was 1/2, times this approximate area. Well, when you add up all these, you are going to get this. I guess when we reduce that, I didn't do those on here, but I'm thinking that's what we got. And then when you take half of that, because that was the width of the interval, we ended up with this. So this would be your final answer. Okay. All right, and number 4, same kind of problem. You do have 7.5 plus sine squared pi t on this interval. The interval 4 minus 2 divided by 4, because it said use 4 intervals, is still 1/2. There's the intervals, there's the midpoints, and then you can do this on the calculator. Let me show you that. You want to make sure that you are in radian mode right there, and we'll quit out of that. And so then we can do 7.5 plus sine. You can't put the squared there. You're going to put it at the end. We're going to put second pi. Whoa, what happened there? Second, and that key, pi, times, I'll just do times 2.25, close, and we're going to square that, and we're going to get 8. So that is how you can put that in the calculator. Let's see if I can put that somewhere. Hold on. Okay, there it is. Hang with me. Okay, so for the calculator, I will have that on the printed notes, and that's what you get is 8. And you actually will get that for each of those. You get 8. You're multiplying it by the width, and so you get 16. And then the average value is whatever our width of our interval was times that area. So we get 8 for the total. Okay. All right, so that should get you on 5-1.